So power supply rejection ratio usually we define as delta change in output with respect to delta change in V in or VDD or VDD. And when we write the transfer function PSRR, PS transfer function, we usually write it a small signal V out of S over okay. So now you have your circuit and can do, let me copy this. So all you need to do, you have to, for a small signal analysis, you have to make this VREF ground. So where will be the input for a small signal here? Where is your input for PSRR? So VDD is your input. So this becomes your V. Now you have to find the transfer function. So apply KCL at V out. So if this is V gate, so what is V gate? So how many currents you have in the output?
3 currents.
3 currents. Which 3 currents?
The current through R1, R2, current through R out, and current through C.
R out, where is, which R out?
R load, sorry.
R load. And third current?
Current to C out.
Okay, so there'll be no current from the PMOS, huh?
Sir, one GM2 current and that R0 of the same PMOS, which comes.
Yeah, basically the current from PMOS will get divided into these 3 branches.
Yeah, so you have to consider the current from PMOS, huh? When you're applying the KCL.
Current. Yeah. Actually, I thought the current going out of that node and the current.
Okay.
I didn't consider the current coming into.
So V out divided by R1 plus R2 so let me just call it R out. So total cap at the output, sorry, total the total resistance at the output is R out, I'm assuming. So, and you have a RC, so what will be that? If I want to write a single, in a single term, what will be that? Okay, let me write it separately. S of C of, correct. But you could have written V out over actually, if you combine the two, and it will be R out multiplied by 1 plus S of R out C out, which is nothing but your omega P out. Okay, ultimately it will come to that when we simplify. Okay, what is the current from PMOS?
GM into V gate minus V in. I mean that is reverse, and this V gate is again GM1 into V out. I mean V out into beta.
into GM2. Okay, correct. So what is V get? Can we tell what is V get in terms of
R. Yeah. It's V out into beta
V out, beta, V out?
into Z of gate, or
Yeah, what is that Z of gate? R gate over 1 plus
1 plus S R gate C gate.
R gate C gate S. Okay. So now you just substitute this and multiply it by V out. So you just substitute this guy here. This we get. And what we get here is V out over R out. So V out we can take common. Your R out come here. 1 plus R out C out S plus GM2. Then you have beta R gate divided by 1 plus R gate C gate S V out equal to GM2 V in.
In V gate expression, don't we have GM1 term?
Which one?
In the V gate expression, writing.
Sorry, wait. That will be GM1. Yeah, correct. So beta GM1. Okay. So now you take V out common here 1 plus. So now what I'll do, I will replace this with omega P gate and omega P out. So I can write this as S over omega P out divided by R out plus GM1 GM2 beta GM1 GM2 R gate divided by 1 plus S over omega P gate equal to so now you need to simplify this V out R out into 1 plus S omega P gate and you get here 1 plus S over omega P out into 1 plus GM1 GM2 R gate R out. And what I'm interested in is V out over V in. So this will become R out GM2 divided 1 plus S over this GM1, GM2, R gate, R out, beta. Can we tell what is this?
Beta and naught.
Yeah, beta and not correct. So 1 plus S over omega p gate. Okay. So if you go back to your impedance, is it similar to that? The only difference is that now you have a R out GM2. Earlier you had a R out, because now you're looking at basically a ratio of the voltages. Earlier you were looking at the impedance. Correct. So now take case 1. Because again, we cannot do the Bode plot for this. So we have to make the approximation that you are looking inside your UGB. And since inside UGB you have only one pole, so we'll do one by one. When omega p gate is dominant and omega p out is dominant, so what would happen to your PSRR curve? So omega p gate is dominant. So what we can do, we can ignore. We can ignore omega p out. So your PSR, PSRR transfer function, which is nothing but V out by V in equal to GM2 around 1 plus S over omega P gate divided by 1 plus S over omega P gate plus beta A naught, and what you get here is GM2 R out divided by so let's assume beta A naught is much larger than 1. Then you can simply write GM2 R out over beta A naught I can write this as omega UGB. Okay. So now I will just break this A naught. So A naught equal to beta, sorry, A naught equal to GM1, GM2, R gate, R out. So I'll substitute this. So what you get? V out over V in. So what will happen? Your R out and GM2 will get cancelled out. So what you get is this 1 over GM1 or get with beta. So what does it mean? What is happening to the DC PSRR? How much suppression you are getting here? Hmm? So in the impedance, impedance was getting DC impedance was getting suppressed by your loop gain. But here, what is the GM1 R gate? Which gain is that?
The op-amp gain, first stage.
Yeah, first stage gain, which means second stage gain basically plays no role in the in your PSRR. So all the PSRR, basically the supply rejection, you are getting only from the first stage or op amp, which means if you want to improve the PSRR, especially at lower frequency, you have to keep the first stage gain much higher. Otherwise, you'll not get very good PSRR at DC. And PSRR at DC, what is that? If I want to define it, what is the delta change in output with respect to delta change in input in terms of DC?
Line regulation.
The line regulation, okay. So the line regulation at any particular, obviously, load current, because it may vary with the load current also, but particular load current, your line regulation will be defined by this, and that will basically, if you want to improve your line regulation, then you have to use higher gain in the first stage, or your error amplifier gain should be high. So now let's look at your AC response, the Bode plot. So where will it start from? What will be the DC gain? One over
Beta G1 or beta GM1 R gate.
one over beta GM1 R gate. And where will it go? It will increase, decrease.
It will increase, sir. No, no. Initially it will be flat and then it will increase.
Yeah, so it will be. So let me use different color. And then you have a 0. It will do like this. And let's say this is my omega UGB. So where will it go? What will be the gain? The gain at UGB. Can we detail what will be the gain at UGB? So go back to your circuit.
Beta A naught by GM1 beta OR gate.
Beta A naught. Sorry, beta A naught by what? GM?
GM1 beta OR gate.
No. Beta A naught by beta GM1 OR gate. Correct. You have a beta term here also in the denominator.
Yes, sir.
So loop gain divided by that. So this will be nothing but your GM2 OR out. Correct. Because beta GM or OR gate will get cancelled out from your loop gain. So leftover will be GM2 OR out. Correct or not?
Correct.
Okay. So now if you want to look at it intuitively. So what happens if you short the gate and apply a signal at V in? What will be the small signal output gain? What kind
It's
of
like a common gate circuit, so it's
it's a common gate circuit, so your gain will be nothing but GMR out, correct? And that's what you are getting here, GM2 R out. Because your feedback is completely broken after UGB and it will peak at GM2 R out, that is the maximum gain, because the first stage has no significance because your feedback is almost broken after UGB. So then whatever the portion you are getting at the output, the input signal, so that will be only contributed by your second stage, and second stage gain is nothing but GM2 R out. So which means it will get amplified actually. So whatever input signal, AC signal you have at the input, that may get amplified if your GM R out is more than 1. So think about you have some ripple at a particular frequency, let's say at omega UGB, whatever omega UGB, let's say you have 1 megahertz, and your ripple frequency at the input is same 1 megahertz. So it's quite possible that if your supply has a, let's say 10 millivolt, 10 millivolt peak to peak amplitude, that basically the noise in the supply, a fixed frequency noise, and at the output it may appear like 100 millivolt or so. So it will make it even worse. So that's why you never keep your UGB around your ripple frequency, because I want to get a very high PSRR, especially. So whatever the frequency range you are interested in for high PSRR, your UGB should be much higher than that. Otherwise, you'll not get any suppression. So now if you talk about, let's say, 1/10 of your omega UGB, then obviously that means the suppression will be 1/10 of GM2 R out. So if your GM2 is, let's say 10, in that case it will become 1, which means you have to further basically go at a lower frequency. I mean 100 times at omega UGB, roughly you will start seeing a good suppression, otherwise not. Which means your UGB should be really very high in order to make sure that you get a good suppression in the um, um, output from, I mean, or the suppression of supply noise in the output. Okay, so what will happen after this? What will happen after omega UGB? So it has a pole, flat. Okay, and then let's say this is your, so this was your omega P gate. This was your omega UGB, sorry, not omega UGB, omega P out. So it will remain flat, and after that you hit the output pole, it will start drop. So if you look, this response in terms of shape is quite similar to your output impedance. And the same thing will happen when you make the output pole dominant. So when you make the output pole dominant, what will happen? It will remain flat until UGB, and after that it will start dropping. So again, in terms of high PSRR, So sorry. So this guy is case 1. And this is your case 2. So now if you see the, PSRR of your when output pole is dominant is much higher compared to your when you make the gate pole dominant. So that's why in both in terms of your transient response and your PSRR, having a output pole dominant will always benefit you. So, but again, as I mentioned, that will always come at the cost of adding an external cap. Otherwise, the only way if you make the output, the gate pole dominant, the only way to achieve high PSRR, you have to extend the bandwidth, or you make your bandwidth so low that your ripple frequency falls somewhere here at higher in the roll off range. That is also one way. So let's say your ripple frequency falls somewhere here in this region. So you will get a separation, but then again you have, in order to make this means you have to reduce the UGB a lot. And but in that case, your omega, the capacitor requirement at omega P gate will be basically very high, and then again it will be as good as making the output pole dominant, so you may not get much benefit. And assume that your input supply has a multiple frequencies, then it may be a problem, because you have a bump here, and this bump will basically cause a problem, this guy. So this bump actually, so this region is a problem for your PSRR. So if you are interested in high PSRR in this range of frequency, then you have to make sure you have enough bandwidth so that your ripple frequency falls in the flatter region rather than falling in this bump actually. So the band pass kind of a looking response. Any questions on this? Okay, so there are certain techniques to improve the PSRR if you make your gate pole dominant. One way is that, okay, so what is happening here actually? If I don't want the GM path, I mean it's actually the GM path which is degrading your PSRR. So somehow if I get rid of this GM, when I say GM is GM2 path actually. So the GM2 portion of the current, if I get rid of that, your PSRR will automatically improve, because in that case you won't get any amplification from your VDD or VIN. So which means if somehow I make sure that when VIN is changing, then the gate also follows the same, which means the effective VGS remains 0. The AC, basically AC voltage you are applying across the gate and source remains 0. Then what would happen? Then it will improve your PSRR. Then you won't have any GM component because effective VGS is 0. Then your current through GM2 will also be 0. So what you do actually, one way is that when you are making this pole dominant, then you connect the C gate with. So which will be better, connecting the C gate to ground or connecting the C gate to VIN? Can anybody tell in terms of PSRR?
Connecting to VIN.
Yeah, so connecting V gate to C in means that capacitor will look like a short between gate and source, and what will happen? Your gate will follow VIN and effective VGS will be 0. So if if you're not using obviously the Miller compensation, if you're using Miller compensation, then you don't have this choice. So in the Miller compensation, your cap will be connected between gate and drain. So in that case, you can't do anything. Then effective cap will appear with respect to ground. So let me change the color. So CC. Improves PSRR, but CC required will be large compared to Miller compensation. So if you are not using Miller compensation, you are simply putting a cap at the gate with respect to ground. Then instead of connecting to the ground, you always connect it to with the VDD. So another way is that you just take the noise from Vin and inject at gate. So you have to do some kind of addition here basically. So you have a current summation at the output. So you take the Vin only when I say Vin only AC component and add at the V gate. So if you add the same amplitude, so you take the basically DC component through feedback, like V gate DC will be based on your feedback, which is the required DC voltage to regulate the output, and take the AC component of V in the same value and the couple them together. Then what would happen? Your effective VGS again will be zero in that case. But you have to make sure your amplitude should be same and your uh, uh, phase will also be same, otherwise they will not cancel each other. So that is more like a improving PSRR using a noise injection actually. But the brute force way is just having a large gap between Vin and gate will help you in improving the PSRR. So in that case, you will get rid of that zero actually, which is causing the increase in this PSRR curve. So by the way, when you say this is increasing, means your PSRR is degrading here, because we have a V out in the numerator and we want this V out by V in ratio as low as possible. So that's why most of the time your PSRR in terms of dB is negative actually. So when it increases in negative, that means your PSRR is improving. And when it is reducing in negative or increasing in positive, then your PSRR is degrading actually. So don't get confused with the term like high PSRR, then more negative means it's lower, not higher. Sometimes people get confused with that actually. Okay. So we'll talk about NMOS LDO. So in the NMOS LDO, what we have instead of PMOS at the output stage, which we call pass element, we have NMOS. And rest of the things will remain same. R1, R2, and you have error amplifier here. So plus, minus, error. This is your VDD or Vin, whatever you can call. And then you have R load, C out, and here you have same R gate, and you see. Okay, so if this is, let's say, I will call it VDD of error amplifier. Okay, or VDD EA, VDD EA. So the one advantage of using NMOS that we know that mobility of NMOS is greater, usually 3 to 4 times in the lower technologies. When you go like, let's say, 180 nanometer or below, you will see like 3 to 4 or even 5 times could be the mobility of NMOS, which means for the same drive strength or drive current, you may require 4 to 5 times lesser transistor. So that main advantage would be like area you will be saving, and another advantage is the C gate which was appearing at the gate will be lower. So your basically pole at the output of error amplifier or gate of your pass transistor will be at higher frequency. So that can help you basically pushing UGB high if, let's say, you want to keep output pole dominant. But if you want to keep again the error amplifier output or the gate pole as dominant, then you have to put a compensation capacitor, C gate. And we cannot use Miller cap here because your output is connected to source, not the drain. So you don't get any gain from the output stage. So can you tell what is this output stage looking like? Which kind of amplifier it is?
Common drain.
Yeah, common drain or source follower, correct. So, and ideally your source follower has a gain of 1. So you hardly get any gain from the output stage. And that's why you cannot use Miller cap here, the Miller effect. So the compensation capacitor you connect at the gate with respect to ground basically will be the actual cap required. So you will not get any multiplication factor there. So the capacitor required may be large, obviously, here because you don't have any Miller effect here. Okay, so but main advantage, as I mentioned, that your size of this pass element will be much smaller. So that's a main benefit you get from this. And then other advantages are R out and or output impedance, and your PSRR is better. That we will discuss one by one. So, but first thing, can we tell what is the limitation here? Can it regulate any output? So, I mean, in the PMOS, let's say we were able to achieve maybe output voltage as high as maybe 100 or 200 millivolt below your VDD. Or in other word, I can say the dropout voltage in the PMOS, you can achieve even 100 millivolt or 50 millivolt. Can we achieve the same thing here? Can we, let's say, if my input is 1.2 volt, can I regulate the output at 1 volt if I have an NMOS? Can anybody tell?
No, sir, because we have to drop out some VTH across in NMOS.
Yeah, correct. So what would happen? Let me just so V drop is VDD minus V out, and your V gate should be what? Equal to V out. So if you go from source towards gate, so you require one VGS here. So your gate voltage required will be, if this is V gate, and one VGS should be, so V gate equal to V out plus VGS, and VGS should be equal to VTH plus what? V overdrive voltage, VOD. Okay, and if this is, let's say, 100 millivolt and this is 500 millivolt, then VGS will be 600 millivolt. Now assume VDD is, okay, so if VDD is 1.2 volt, V out is 1 volt, let's say. So your required gate voltage will be 600 millivolt plus 1. So 1 volt plus 600 millivolt. Which means if this is the gate voltage required, then your VDD of error amplifier VDD of should be greater than 1.6 volt. Okay. So which means if I keep the same VDD, I cannot regulate the output until unless your dropout voltage is very high. So if your dropout voltage is very high, obviously, let's say your dropout is 600 millivolt. So let's say your VDD is 1.6, output is 1, then you have a 600 millivolt, then V get required will be 1.6. So, I mean, so you'll be at the edge basically, which means your error amplifier will saturate at VDD, which you don't want. So it should always be greater than that. So which means if your dropout voltage is more than 600 millivolt here, only then you can regulate the output, otherwise you cannot. So for large dropout, you can do that, but for smaller dropout, NMOS regulator won't be able to regulate unless you use a higher VDD for error amplifier, and that's why most of the time when you use NMOS regulator or LDO, what you do, generate a separate supply VDD for error amplifier, and that can be generated if you have a single supply. Let's say the VDD which was 1.2 volt and you require 1.6 volt, so you need to boost it, so you require capacitive charge pump. Or in your on your system, let's say you have a 1.2 volt and 1.8 volt both, then you can hook up your error amplifier to 1.8 volt. So that's what you need to do. larger than VTT to be boosted or for V drop greater than VGS. Will be less than VDD. Okay. So let me copy this. So if this is, let's say, 1.2 volt, this guy is 1 volt, then this 1.8. So switch cap charge pump will talk when we later in the course when we discuss about switching regulators.
Sir, I have a question.
Mm-hmm.
So when the dropout voltage is large, say it's
Mm-hmm.
greater than 2V overdrive plus VTH, which is
Mm-hmm.
in this case.
Mm-hmm.
So in that kind of a scenario, do I go for, I mean, is there a metric to select if I go for a switching regulator or a NMOS linear regulator? Or rather, like efficiency wise, if I have a dropout, I mean, if the dropout is large, efficiency wise, is this a good choice?
No, it's not a good choice. But as I mentioned earlier, when you have a bigger system, you will have multiple modules, and some module may require large current, some module may require smaller current. Okay. So let's say from 1.8 volt, you want to drop to 1 volt, for example. So, and that 1 volt you are supplying to a module where load current is, let's say, 10 milliamp or so. But your system, total system current required may be 10 amp or so. So 10 milliamp, even if your efficiency is, let's say, 30%, 20%, or 50%, overall system efficiency may not get impacted because it's only a fraction of power you are delivering to that module. Okay, so efficiency will matter mostly when the power you are delivering from that regulator is a large fraction of your total system power.
Okay, sir.
Okay. So, but let's say you are supplying to a module which requires 1 amp or 2 amp. Obviously, I mean, using a large dropout is not a good idea in that case. That's why I mentioned that for large current, you prefer a low dropout regulator like a 50 millivolt, 100 millivolt kind of dropout. And if you have a large dropout, then you can use linear regulator only in the case where your load current is small. But for large load currents, you always prefer a low dropout. And if your dropout is large, then you have no choice but to go to switching regulator for better efficiency for higher load current applications.